Hello, dear students. This is a second lecture describing the concepts in statistical thermodynamics. Myself, Dr. Sharayu M. Thorat, Associate Professor, Sri Shivaji College of Arts, Commerce and Science, Akola, is here with some of the further concepts. In this, first we are going to discuss some of the numerical problems based on probability. Now, for example, let us discuss the first problem. Calculate the number of ways of distributing distinguishable molecules, suppose A, B, C, between the three energy level so as to obtain the following set of occupation number. So that means the three molecules, suppose N0 is equal to 1, N1 is equal to 1 and N2 is equal to 1, that is each energy level is occupied by one molecule. So you have to find out the number of ways of distributing the distinguishable molecules. So that is calculated by the formula of probability, that is W is equal to factorial N divided by N0 factorial N1 factorial into N2 factorial. Now where this total number of molecules N is equal to 3, N0 is equal to N1 is equal to N2 is equal to 1. That means each energy level should be occupied by one molecule. So substitute the value in the formula of probability. W is equal to the value of factorial N. N is 3. So 3 factorial divided by N0, N1 and N2 are all equal to 1. So 1 factorial into 1 factorial into 1 factorial. So that is, let us calculate that. 3 factorial means 3 into 2 into 1. And 1 factorial means 1 into 1 into 1. So the total answer comes out to be 6. That means there are 6 ways of distributing the 3 molecules, that is ABC, as required in the problem. Now the same result can also be obtained by considering the following treatment. For example, the energy state, the energy value are given by epsilon 0, epsilon 1 and epsilon 2. Okay, and N1 cap n is equal to 1, n1 is equal to 1 and n2 is equal to 1. And these are the 6 different configurations in which these molecules can be arranged. So first configuration, second configuration, third, fourth, fifth and sixth. So there are 6 ways, that is 6 configurations in which the molecules ABC can be arranged. For example, let us discuss the first configuration. In the first energy level, A is present in the second energy level, B, the third energy level, C. Okay. Now here ACB, BCA, BAC, CAB and CBA. That means there are 6 possible configurations. These are the 6 possible configurations in which the molecules can be arranged in different ways. So this was the first problem based on the probability. Now let us discuss the second problem. Calculate the number of ways of distributing 4 molecules in 4 energy levels. So as the distribution should be 2 molecules in the energy level epsilon 0, 1 molecule in the epsilon 1 energy level, 1 molecule in the epsilon 2 energy level and 0 molecules in the epsilon 3 energy level. That means N0 is equal to 2, number of ways, N0 is equal to 2, then N1 is equal to 1, N2 is equal to 1 and N3 is equal to 0. So we have to distribute the 4 molecules in 4 different energy level such that 2 molecules should be in first level, that is given by epsilon 0. Then epsilon 1 energy level will have 1 molecule, epsilon 2 energy level will have 1 molecule. So 2 plus 1 plus 1, 4 molecules. And 0 molecules in the fourth energy level, that is epsilon 3 energy level. So that means N0 is equal to 2, N1 is equal to 1, N2 is equal to 1 and N3 is equal to 0. So now the solution, the probability equation, W is equal to total number of molecules, that is 4. So factorial 4 divided by the ways it should be arranged are 2 molecules. So 2 factorial into 1 factorial into 1 factorial into 0 factorial. So these are the different ways of arranging which we have written. So let us solve the problem. Factorial 4 means 4 into 3 into 2 into 1. Factorial 2 means 2 into 1. And factorial 1 means 1 into 1 into 1. So the total answer comes out to be 12. Now you can see the 12 configurations here. Since the value of thermodynamic probability comes out to be 12. Now these are the 12 different configurations. 1, 2, 3, 4 up to 12. So there are 12 different ways or 12 configurations in which the 4 molecules has to be arranged. Okay, out of that the first energy level epsilon 0 will have 2 molecules. So see, in all the 12 configuration 2 molecules are arranged in the energy level epsilon 0. Then the second energy level, that is epsilon 1, will have 1 molecule. The third energy level, that is epsilon 2, will have again 1 molecule. And the fourth energy level, which is given by epsilon 3, will have 0 molecule. So whatever answer we have got from the probability equation, the same can also be arranged in this particular way. Now let us discuss the third problem. Calculate the number of ways to distribute. So there are 4 conditions given here, 4 cases. Calculate the number of ways to distribute. In first case, 2 distinguishable objects in 2 boxes. Second is 2 distinguishable objects in 3 boxes. The third case is 2 indistinguishable objects in 2 boxes. And fourth is 2 indistinguishable objects in 3 boxes. So these are the different ways in which you have to arrange, okay, the objects. So the solution is, now let us discuss for first 2 distinguishable objects you have to arrange in 2 boxes. So the number of objects n is equal to 2. Okay. Then number of boxes, that is location, is also 2. So the number of configuration is given by the formula W is equal to L raised to the power n. So 2 raised to the power 2, that means 2 square, so that comes out to be 4. That means there are 4 ways to distribute 2 distinguishable objects in 2 boxes. Okay, so we have calculated the answer to the first case with the help of the simple formula W is equal to L raised to the power n, where L is, small l means number of boxes or location, that is 2, and capital N means the number of object, that is also 2. Now let us discuss the second case. You have to arrange 2 distinguishable objects in 3 boxes. So again you have to use the same formula. N is equal to again 2 objects, but the boxes location is 3. So the value of L is 3. The formula is thermodynamic probability W is equal to L raised to the power n. So the value of L is 3 and value of n is 2. So 3 square, so 3 into 3, that means 9. So there are 9 different ways to distribute 2 distinguishable objects in 3 boxes. Now let us turn our attention towards indistinguishable objects which are to be arranged in 2 boxes and 3 boxes. So for this the formula is changed. So for the third case, 2 indistinguishable objects in 2 boxes. The formula is W is equal to n plus L minus 1 factorial divided by n factorial into L minus 1 factorial. Now let us substitute the value. The value of n is 2. The value of L is also 2 minus 1 factorial divided by the value of n is 2. So 2 factorial. L minus 1. So 2 minus 1 factorial. So if you solve this, 2 plus 2, 4 minus 1. That means 3 factorial. So the value of 3 factorial is 3 into 2 into 1. Similarly, 2 factorial, the value is 2 into 1. And 2 minus 1 means 1 factorial, the value is 1. So if you solve this, the number of ways comes out to be 3. That means there are 3 ways to distribute 2 indistinguishable objects in 2 boxes. Now the fourth one, in this case you have to arrange 2 indistinguishable objects but in 3 boxes. So the formula is same here as we have used for the third case. Thermodynamic probability W is equal to thermodynamic probability W is equal to n plus L minus 1 factorial divided by n factorial into L minus 1 factorial. So substitute the value of n as 2, but here the number of location boxes is 3. So the value of L is 3 minus 1 factorial. The value of n is 2, the value of L is 3. So substitute in the same formula for the fourth case. The answer is 2 plus 3, that is 5 minus 1, so that is 4 factorial divided by 2 factorial, 3 minus 1, 2 factorial. Now 4 factorial means 4 into 3 into 2 into 1. 2 factorial means 2 into 1. Again 2 factorial means 2 into 1. So if you solve this, the number of ways to distribute comes out to be 6. So there are 6 ways to distribute two indistinguishable objects in 3 boxes. So by discussing this problem, we come to notice that if you have to arrange distinguishable objects in some specific location, then the formula is W is equal to L raised to the power n. But if you have to calculate the number of ways for indistinguishable objects in different location, that is 2 boxes or 3 boxes, then you have to use this formula. W is equal to n plus L minus 1 factorial divided by n factorial into L minus 1 factorial. So these are the simple problems which can be asked on thermodynamic probability formula. Now let us move forwards towards understanding the concept of probability and entropy. The scientist Boltzmann showed that the entropy S and the thermodynamic probability W are related by the equation S is equal to K log of W, where S, that is the entropy S, total entropy, is a function of thermodynamic probability W total. So that is a function of WA into WB. That means thermodynamic probability of state A into thermodynamic probability of state B. In this equation where K is the Boltzmann constant and capital K is equal to R divided by Na. R is the gas constant and Na is the Avogadro's number. The validity of this equation 6.6 can be demonstrated in the following way. Consider two thermodynamic systems A and B. Now let the entropies of the two systems be given by SA, that is SA is the entropy of system A and SB is the entropy of system B. Let WA be the number of configuration, that is the thermodynamic probability of the system A, and WB is the thermodynamic probability of the system B. Now since the entropy is a measure of randomness in the molecular system, so the larger is the randomness, so larger is the number of configuration. Therefore, we consider that entropy is a universal function of configurations or probability. So thus we can write entropy S is a function of thermodynamic probability W. And individually, entropy of system A is said to be a function of thermodynamic probability WA and SB is a function of thermodynamic probability WB. When the systems A and B are combined, then the entropy of the final state is the sum of the entropies of each system. Because entropy is an extensive property, so we can write the total entropy, that is S total, is equal to entropy of system A plus entropy of system B. Now the probability of the combined system is the product of the probability of the systems A and B. That means if you have to calculate the total thermodynamic probability W total, then you have to write probability, that is thermodynamic probability of system A into thermodynamic probability of system B. And the total entropy S total is equal to function of total thermodynamic probability, that is W total, which is written as function of WA into WB. So since total thermodynamic probability W is given by WA into WB, here we are writing WA into WB. Now the total entropy is equal to SA plus SB. So for SA, we have to write F of WA plus F of WB. So that means from equation 6.7 and this equation 6.8, we can write the function of WA into WB is given by the individual function F of WA plus F of WB. So this relation is having the form log of x into y is equal to log of x plus log of y. So therefore, a single valued monotonically increasing function with this property is f of w is equal to k log of w, where k is a universal constant known as Boltzmann constant, and the expression for entropy related to the probability is the same as shown by the equation 6.6, that is S is equal to k log of w. So equation 6.6 enables us to have a physical concept of entropy. That means at absolute zero, all the molecules would occupy the ground energy state, and hence there is only one way of arranging the molecules in the various energy level. So that means thermodynamic probability is equal to 1 at absolute zero, and hence the entropy S will also be zero, which is required by the third law of thermodynamics. But as the temperature increases, the molecules would tend to occupy the higher energy levels, and hence the number of ways of arranging the molecules in various energy level would increase, and hence k log of W would also increase, and consequently the entropy value would also increase at higher temperature. That means greater order means smaller number of ways of arranging the molecules. And similarly, greater disorder means large number of ways of arranging the molecules. So this greater entropy means greater W and hence greater disorder. So hence entropy may be considered to be a measure of disorder or randomness in the system. So the concept of entropy, which we know, that is explained by with the help of this statistical thermodynamics. Now let us come back to the revision of system, assembly and ensemble. If we have a collection of particles, then each particle is called as a system, and the collection of particles as a whole is called an assembly. Now what is ensemble? The energy of a molecule keeps changing with time due to the intermolecular collisions, energy transfer and motions to spaces. So it is necessary to take the energy of a molecule as the average value over a certain time. So to do the impossible task of time averaging for a system containing of the order of an Avogadro's number L of molecules, Willard Gibbs introduced the idea of ensemble. So consider a system and the surroundings with which it is in contact to constitute a distinct unit. So an ensemble is formed by reproducing this distinct unit many times. The ensemble is a set of imaginary replication and is a mental construction. So each member of the ensemble is subject to similar, that is same thermodynamic constraints as the original system. And the number of replicas can be as large as we want, and when it is appropriate, the number can become infinite also. So there are three types of ensemble. First one, when the units are separated by impermeable adiabatic walls, the energy of every system is the same, and the ensemble is called as microcanonical ensemble. For example, the number of molecules capital N, the volume V, and the energy of the units, that is E, will be the same in all the units. So if you see the figure next, you can understand this microcanonical ensemble. Now see, this is the microcanonical ensemble. Okay, so this is an ensemble which is made up of a different system, okay, of many assemblies, and each assembly is having different systems. So that is a microcanonical ensemble. Now in this microcanonical ensemble, you can see when the units are separated by impermeable adiabatic walls, the energy of the every system is same. You can see here. Okay, energy of the every system is the same. Then the ensemble is called as microcanonical ensemble. Okay, this microcanonical ensemble is having 35 systems. Okay, if you count this system, the answer comes out to be 35, and each system is having same value of energy E. Okay, and also the number of molecules N and the volume also remains the same in all the units. So such a type of ensemble where the number of molecules n, then the volume V and the energy E remains same for each system, then this type of ensemble is called as microcanonical ensemble. Then the next is the canonical ensemble. Okay, again here there are 35 systems, but here the energy values are fluctuating. Each system is having same value of total number of molecules n, the volume remains the same and temperature remains same, but here in case of canonical ensemble, the units are separated by diathermic walls, letting the energy fluctuate about some average value. But the temperature and the volume and capital N remains the same. So here the energy is fluctuating, hence each system is having same value of N, V and T. Okay, so such a type of ensemble is called as the canonical ensemble. Now see the third type, that is the grand canonical ensemble. The third type of ensemble is based upon the open system. So each system here is an open system where the number of molecules in the unit is not maintained constant. So here you can see capital N, that is the number of molecules are not constant since the system is made up of open system. While volume V and temperature T and also the chemical potential mu, it remains the same in all of the system. Okay, so in grand canonical ensemble, what is constant? Chemical potential mu, volume V and temperature T is constant for each system, whereas the number of molecules N are different because the system is an open system. In canonical ensemble, the total number of molecules N, volume and T are constant, whereas in microcanonical ensemble, the total number of molecules N, volume and E are constant. So this was all about the different type of ensemble, that is microcanonical ensemble, canonical ensemble and grand canonical ensemble. So again in this second lecture we have discussed some of the conceptual information about the statistical thermodynamics. We will keep posting the other lectures soon. Thank you.